Greetings, scholars. This is the graphing video for the Physical Sciences class. This video is just going to go over a couple of topics that were in the online school that I thought were important to cover before you started your first lab. And the first topic I'm going to go over is the significant figures or the significant digits topic. And I just wanted to make that hopefully a little bit clearer by using some examples. Here we have our ruler. And you can see that the ruler is a centimeter ruler, and it is also divided up into smaller units. Those are the millimeters. And we are going to use our ruler now to measure this nice little green blob. So we make sure that our ruler, that the 0 mark on the ruler lines up with one edge of the item that we're measuring. And then we're going to take a look at how far over our other edge lines up on the ruler. And you can see it's not quite a full centimeter. It is 5, 6, 7, it's somewhere between 8 and 9 millimeters. So 8 millimeters is too small. It's greater than 8 millimeters, whatever that side of the square is, but it's also less than 9 millimeters. Okay, and at this point, we run out of measurements or tick marks on the ruler. So we have to guess. We know it's 8 something, but we're not entirely sure what. It's 8 point, and I'm looking at, and I'm going to say it's almost 9, so I'm going to call that 8.9 millimeters. Okay, and this is a pretty standard practice. When you're measuring something, you look at your tool, the tool that you were using, you look at how fine the measurements are, the smallest measurement that is on the tool, and then you're allowed to guess one more, because the human eye is actually pretty good at dividing up those spaces and guessing at the next one. So you can see that given this particular tool, this ruler, that 8.9 millimeters is pretty reasonable. We've got the millimeters there, and we're only guessing at one spot. We're only guessing at one spot. But if we were to say that it was 8.9467 millimeters, we would really need a much better tool than what we have here. So when you're using your rulers to measure how far the ball bounces, you need to think about what your ruler can actually measure, what your meter stick can measure, and what you can see. Because as you can see, to say that using this ruler, using 8.9467 millimeters doesn't make sense. This ruler does not allow for that fine of a division. So when you're using your equipment, I want you to go to the smallest division that's on the tool you're using to measure, and then one guess. Right? And that's tied into the significant figures. And again, in the higher sciences, when you get into physics and chemistry, there are mathematical rules that govern when to use it and when not to. But it's pretty standard that look at the divisions on the tool, on the piece of equipment you're using, and guess one. So let's look at this dynamometer down at the bottom, which is measuring in grams. So you can see that it's mass. And you can see that the first big tick mark is 100 grams. That's a big chunk. And there are 1, 2, 3, 4, 5 spaces in between. So each one of these little spaces is going to be 20. So it's going to be 20, 40, 60, 80, 100. Okay, so we can say something is 20, or we can say something's 40, but now this space in between is a little bit nebulous because it's not really evenly divided. So this is the kind of thing where I think you could probably divide that space up into 4 pretty well and go, 20, 25, 30, 35, 40. But with this piece of equipment, you're not going to get very exact measurements. And I just want you to be aware of that. I'm not looking for, when you're doing your lab experiments and you're asked to use this and talk about the mass of something, if you give me something that says 22.59 grams, I'm going to ask to see what piece of equipment you're using, because this is just not that good. Okay, this is not that exact. I'm choosing my words very carefully here because the other topic that I wanted to talk about was the difference between accuracy and precision. And when I think of precision, I think of like a doctor doing surgery is very precise, or an engineer designing something, they're very precise, or a robot doing some fine tuning, like maybe on a circuit board, they need to be very precise. And that's not exactly the best usage of that word, but it's the common usage. It's what I think of and probably what you think of too. In science, we have accuracy and precision. I'm just going to put an A up here for accuracy and a P for precision. And they mean slightly different things. If something is accurate, it is on target. It is where it needs to be. So you're hoping that your doctor is very accurate, or the engineer was very accurate when they designed the space shuttle, that all of their figures lined up just right. Precision is a different thing, and it mostly means predictability, consistency. So you can see these two groups of dots here. If this big circle is a target, our blue dots are very accurate if you're aiming for the middle of the circle, because they're hitting right in the middle. Our green dots are not accurate. They're not as accurate as the blue dots, but they're precise. They're grouped tightly together. And what that precision, that consistency of the grouping allows us to do is to alter what we're doing so that we can get them accurate also. So when I think of precision in everyday usage, I usually think of accuracy and precision together. That not only is it very detailed, but it's also right on target. And that's just one of the things I wanted to point out. But we're looking for precision to be, how predictable is it? Because if it's predictable, if you were shooting these arrows and you were consistently shooting over here, you would know that you would have to change something. And once you figured out what needed to be altered, you could get those green arrows to be both accurate and precise. It's like your technique is good, it's just off a little bit. When you're looking at your laboratory data and you're collecting data for the different trials, the one thing I want you to look at is how close, how consistent are your results. So that's just accuracy and precision. And again, in common usage, I would assume that if something is precise, it's also accurate. But that is not necessarily so. You can be precise in science and be off the target. Okay, what that means is how predictable and how consistent your data is. Okay, it may be totally off target, but if you're doing it consistently, then that gives you information about how your lab is going. Okay, and it may give you information about your hypothesis. If you are consistently getting something you don't expect, that should be telling you something. So I love science, because if you're not sure, you can always rejigger it and play around, and sometimes a lab will lead you to other questions. And that's really cool. Labs don't have to be finite. They don't have to end here. They can keep going. And maybe some of our labs will show us that. Finally, we're going to look at what we're going to do with our data. And this is the graphing part. So we've done a quick run through significant figures. We've talked about that if your ruler measures only to millimeters, we don't want you to give us 0.55555 millimeters as a measurement. That's just way too detailed for what your equipment allows. We've talked about precision and accuracy, and that precision is what we're going for. We're going for that predictability in our data. Okay, if it's accurate, that's a bonus. But if it's not, but we have nice, precise data, that does tell us something about our procedure and our lab, and we need to figure out what that is. So just like if you were an archer and you were constantly shooting the arrows up and to the right, you would know something needed to be adjusted to get them down where you need them to be, that there's something else you need to do. So not all of your labs are going to end when you're done. Isn't that cool? Okay, next up, let's look at your data. I have a little chart here over on the left-hand side, and I'm going to be talking specifically about the drop and bounce lab. That's the one you're going to be doing first. D is the drop height, and I'm just going to use 40 centimeters as my first piece of data. We're going to be dropping everything from 40 centimeters, and we're going to look at our rebounds. And let's say the first time it bounced back 18 centimeters. The second time, maybe 20. The third time, 22. All right, so these are pretty close. They're not too far off. Again, for the equipment that we're using and for how fast you can actually look at the ball rebounding, this is probably really good. Though we'll know more after we go over all of our results in class. But just for now. Now, if your results were like the first drop was 5 and the next one was 25 and the third drop was, for some reason 45, you would look at these and say, okay, they're all over the board. There's something going on here. We don't have that precision. There's something wrong in our technique because our results are not consistent. So I want you to take a look at your data as you're doing it. And I don't want you to throw data out. Okay. But it's okay to say, okay, I got this for 40. And then I realized that I was dropping differently. Maybe I was spinning it and it was going off to the side too much, making it really hard to measure the height. Maybe I was getting frustrated and I actually didn't drop it but threw it down. I could think of a couple of different things that could have gone differently, but you need to look at that and be consistent with your method and technique. So if you're getting data like this and you think you might figure it out, it's okay to say, okay, this data didn't work. And make a little note of it that, this was just inconsistent. I changed my technique here. I started measuring all the way from the bottom of the ball, and it got more reliable, more consistent for me. And so you do want to check out your data. You are looking for that consistency. All right, so we've got the drop height of 40. We've got our rebound of 18, 20, and 22. Of course, I picked those numbers because they have a nice even average of 20, which is what's going to go in my final column here. And we are going to put these onto a graph to see if there's a relationship. Okay, and graphing is a great visual way to look at our information, look at our data points, and see if there's something interesting going on there. Are they related? Does it make sense? And of course, since this lab is supposed to prove that point, it really does. Along our x-axis, we've got our independent variables, and I'm just going to abbreviate it. Independent. Okay, and that is just a convention that the x-axis is where our independent variables go. Along the y-axis is our dependent variable. And now we need to decide which one is our independent and which one is our dependent variable. Okay, we've got the drop height and the average rebound. Okay, so these are the two pieces of data that we're going to be graphing together. Now the independent variable, let's say we have this great function machine kind of thing here, and this is the lab procedure. And we're going to input something, and we're going to input the independent variable, a lovely handwriting, and we're going to output the dependent variable. Okay, our independent variable is the number that we're going to put in, and our lab procedure is going to muck with it and do all sorts of weird things to it, and then out comes our dependent variable. Out comes our piece of data. Okay, so from this little goofy analogy, hopefully you get that our independent variable is the drop height. That is the thing that we are controlling. That is independent of the procedure. That variable doesn't change because of whatever we do in our laboratory procedure. The drop height is what goes in. That's the piece of data that is independent of our lab procedure. Okay, we pick it. I believe in the drop and bounce, we're doing 20, 40, 60. We're doing it in 20s. We could pick 30 if we wanted to. Okay, it's totally independent of the procedure. The dependent is dependent on what that function is, what's going on in the procedure. And that is the rebound. Okay, it is totally dependent on whatever is happening in the lab procedure. So we're going to graph that. We've got 40 for our independent, so that goes along the x, and 20 for our rebound, our average rebound, and we're going to put a point there. And we're going to take the rest of our data, and we're just going to add points wherever they fall. And I'm just making these up. pretty much wherever they fall. We're going to say, okay, you know, there's kind of a relationship here. They do pretty much go up, except for this one. We might want to check that out and see if there's anything going on there. But for now, and we're going to draw a line of best fit. Okay, now a best fit line does not necessarily have to include any of the points. Okay, it doesn't have to include our data points. What we're looking for is what best represents that particular relationship that we see. So we're looking for any points that are above the line to be balanced out by the points that are below the line. So we're looking for, you know, maybe I could have made this one even better because this one's really low. Okay, so there's not necessarily going to be a right line or a wrong line. We're looking for a general relationship. Again, and with our equipment, we're not going to get anything perfect. So what's important to know about a best fit line is that these points do not have to be on the line, and you're just trying your best to make sure that the overs and unders balance out. Right? From this point in our data collection, we are actually going to write the equation for that graph. And we're going to do that in slope-intercept form. There we go. Y equals mx plus b. Because one of the things we're going to be looking at in our laboratories is our y is our outputted data, what we get out. Our x is what we put in. And we're looking to see if this m and this b actually mean anything. Okay, what kind of information can we glean from their relationship? And that's what we're going to be interested in looking at. So what I'd like you to do is make sure that you do your lab and do it in a safe place. Now we're just dropping balls, but even drop balls can end up all over the place. So make sure you do it in a safe location where you've got space to do it. Make sure you clean up the balls after yourself because you don't want anybody to slip and fall on them. Read the lab safety section in your lab manual. If you don't have a lab manual that's printed out, there is one on the online school that you can access. And I expect you to follow all of these safety precautions so that nobody gets hurt. Again, this is it's not very likely that you're going to get hurt during this one, but please do some common sense preventative things. Make sure you clean up the balls, put them away, and take care of it. Then I would like you to make sure your data is in a nice chart form and graph each of your charts as well. And this is what I would like you to bring with you to class on Wednesday so we can talk about your lab. Okay, take care, have fun, and if you need anything from me, please zip me an email.